Greetings everyone, this is Brian Jump. In this presentation, I'm going to cover signal processors, equalizers, reverbs, and dynamics. Okay, the main point is that signal processors are used to amplify, alter, and improve the sound of songs, sound designs, and videos. Any piece of audio can be manipulated using signal processors. So knowledgeable use of these devices is a required skill for professional audio engineers. If you want to go into sound recording or producing, you need to know how to use your signal processors, especially these three: equalizers, reverbs, and dynamics. The most common signal processor is the equalizer, which is an electronic tone control device that alters sound by increasing or decreasing volume at specific frequencies. The tone knob on an electric guitar is a kind of equalizer. That's me just manipulating the tone knob. It's a very simple equalizer. So an equalizer is an electronic tone control device that alters sound by increasing or decreasing volume at specific frequencies. Because of this, they're sometimes called spectrum processors. So here's a picture of an equalizer, a real simple graphic equalizer. And up here we have frequencies. And then these are long throw faders that allow you to increase or decrease the volume. Say you want to increase 125 by 6 decibels. That's going to give you significantly more bass. Or maybe you want to turn 8,000 down. Same idea. Significantly less treble. An equalizer is an incredibly powerful tool. You can really manipulate the sound of your audio. So most equalizers extend from 20 Hz to 20,000 Hz, because that corresponds to the range of human hearing. So you can think of an equalizer as a volume control device designed to affect specific frequencies. Okay, there are three kinds: fixed frequency, parametric, and graphic. Let's take a look at the fixed frequency equalizer first. Fixed frequency equalizers typically have three knobs labeled bass, mid, and treble, or low, mid, and high. You might find them on your car stereo. They're often encountered on guitar amplifiers. And you always know that you're dealing with a fixed frequency equalizer if you see three knobs labeled bass, mid, and treble, or low, mid, and high. Although they are useful in some contexts, fixed frequency equalizers are not especially useful to music technologists and audio engineers. They are blunt tools, not precision. They're nice to have on your car stereo, and they're marginally useful on guitar amps, but that's where their utility ends. The problem with these devices is that they are not adjustable for specific frequencies, hence the name. They are fixed. So the mid knob on a fixed frequency equalizer is usually set around 1000 with a fixed Q width. So here's 1000 on an equalizer. On a fixed band equalizer, the mid knob will never be anywhere else than 1000. Say you wanted to adjust a notch at 2000. Well, tough. You don't get to do that with this equalizer. That's why they're not professional audio. They're fixed. Also fixed is this curve. You can't tighten this curve up or widen this curve with a fixed frequency equalizer. They are set and immutable. So they often affect a large swath of frequencies at the frequency at which they are centered. So it's not only affecting 1000, but all the way down to, 300, and then all the way up to 4000. Can't change that curve with a fixed frequency equalizer. So you can never do this. Notice how this is nice and tight. Nice clean notch. The fixed frequency equalizer does not allow you to do that. So they're better than nothing, but not much. They're basically useless in a pro audio context. If you're going to use an equalizer for mixing or mastering, you need to start with a parametric equalizer. Okay, and a parametric equalizer allows audio engineers to select any frequency in the sound frequency spectrum for adjustment to manipulate the width of also affected frequencies. It's a big improvement on the fixed frequency variety. Now, superficially, a parametric equalizer resembles a fixed frequency equalizer in that it often has knobs labeled low, mid, and high, or high, mid, and low. But unlike the fixed frequency equalizer, the parametric equalizer also has a control knob, or knobs, for selecting specific frequencies. And most also have a control knob for adjusting the cue width. Okay, so look, low, mid, high. What's this, a fixed frequency equalizer? No, it's not, because first of all, we can adjust the frequency. This one's set at 20, but I can move this knob and make it anywhere. And this one, you can also move it anywhere. And then there's this other knob that allows you to adjust the cue width. Remember, this is the cue width. This one's tight, this one's wide. That's cue. Parametric equalizers and graphic equalizers are essentially the same thing. They basically only differ in their interface. Indeed, sometimes with a plugin, you'll see a graphic equalizer and a parametric equalizer in one unit because they are essentially the same. Often, graphic equalizers have sliding control faders, like what's depicted here. Some have 8, 16, some have many more. They allow you to visually sculpt the cue. So notice that I have this graphic equalizer set in something resembling this shape here. So this is a graphic equalizer in a digital interface or a plugin. But back in the day, these were actual devices with these fader knobs. But the idea is the same. You can sculpt the size of your cue. You can select a center frequency. This is a 7-band equalizer. Not exactly the greatest piece of gear, yet it's still better than a fixed frequency equalizer. Nowadays, of course, the graphic equalizer allows you access to any frequency, and the parametric equalizer is there in case you would rather use it. But they are the same devices. This is Studio One's Pro EQ. Most DAWs have an equalizer which operates similarly. Okay, so now that we know that there are 3 types of equalizer, fixed frequency, parametric, and graphic, let's take a look at how you use them. And as it happens, there are 3 ways to perform equalization. This is a story of 3s. You can do notching, or shelving, or filtering. So here's a picture of an EQ, a graphic EQ with a notch. Look, it even looks like a notch, like you swung an axe, made a notch. It's centered around 1000. It's pretty tight as far as its cue goes. This is a real common way to use your equalizer. Keep in mind, you could go up too, so we could boost 1000. But this graphic equalizer has a cut at 1000. They're both called a notch. A shelf is done when all frequencies at or below or at and above are increased or decreased by the same amount. So this is at 500, and then everything above 500 has been affected equally. Notice that it even looks like a tabletop or a shelf. Now this one is a boost, but you can imagine this could be a cut. You could have the shelf down here, and then everything at 500 and above will be affected, creating this shelf-like curve. And finally, filtering is a method of equalization that allows you to completely remove a frequency. So it looks like right around 220 has been completely removed. Notice how it's different than a notch. The notch doesn't go all the way down. Here we have 220 completely turned off. So this is a notch filter. There are ways to perform filters that look more like shelving, and they are called low pass and high pass filters. So now instead of selecting a single center frequency and notching it or eliminating it, now all frequencies at or below or at and above have been turned off. Not turned up or down like a shelf, but turned off. So here we go. At 200 and below have been filtered. That's called a high pass filter. That's because the high frequencies are allowed to pass. The high frequencies get the hall pass. They're allowed to roam and exist. On the other hand, we have a filter set at 2K at 2K and above have been turned off. That is a low pass filter. Because look, all these low frequencies get to exist. These low frequencies get the hall pass. Now if you dial both in, you get what's called a band pass filter. So now we have a bunch of low frequencies attenuated and turned off, and a bunch of high frequencies attenuated and turned off. Now the result of this type of equalization, a band pass filter, is a sound that seems to emanate from a tiny transistor radio style speaker. So if you're looking for a special effect, a bandpass filter is a pretty powerful way to use an equalizer. Notch filtering and bandpass filtering are sometimes used for corrective endeavors instead of creative ones. If you have a busted piece of audio, you might have to get in there with filters and remove sounds. Maybe there's some interference. I'm afraid that's my PA system, which is on, that my guitar is plugged into, has this low frequency sound emanating from it. I might have to filter that out when I produce this video. Now that we know what an equalizer is and how to use it, let's take a look at the signal processor responsible for simulating the ambient character of halls, rooms, and theaters, and other commodious spaces, known as reverb. Okay, reverb is a signal processor that simulates the ambient sound produced in a performance venue, or any space, really. Common rooms that are simulated are halls and theaters, cathedrals, churches, any space imaginable, really. Tunnels, canyons, wells, and so on. The reason you need reverb in a studio context is close miking, whenever you're very close to your microphone, produces a very dry character of audio. And that's not how we're used to experiencing music. We're usually in some sort of performance space. So the ambience, or reverb, needs to be added artificially. At bottom, reverb is operated by delay, which is an electronic process of copying an audio signal and playing it back later. Very clean echo repeats. Indeed, you can use delay to simulate ambience if you want a more streamlined effect. So digital delay is the foundational effect responsible for reverb. By layering multiple overlapping delay repeats, a performance space can be simulated. So delay units create echoes in which the repeated sounds are clear and distinct from the primary sound. To hear delay in your mind's ear, imagine yelling an abrupt and sharp and loud syllable into a canyon. You hear that echoey bounce in your mind's ear? That's delay. Reverb and contrast is an effect in which the primary sound and its echoes are blended into one hybrid, all-encompassing ambient sound. So imagine the same barked syllable inside a cathedral or a church. That's reverb. In nature, reverb occurs when a sound hits a surface, echoes back to the listener, and combines with the primary sound. Sound reflects off surfaces in this way until it loses all its energy. In some listening spaces, this may take several cycles of bouncing and reflecting chaotically before it finally dies away. Natural reverb erodes gradually as its reflections lose energy, usually over a period of seconds. So reverb is created electronically by adding multiple randomized delay repeats to the original sound. Vocals, instruments, and other musical sounds often benefit from the application of a modest amount of reverb. So modern reverb plugins allow you to adjust the scale and scope of a performance space. This is the Room Reverb plugin in Studio One. And this box in the center is the scale and scope and shape of the room. And you can change the room size, the width and height. You can even change the geometry. There's many presets. You can select tunnels and cathedrals and theaters and rooms. Now, the most common adjustable elements found on reverb units include pre-delay, initial reflections, room size, and reverb time. There are others, of course, but these are the big ones. So it's important to have some idea of the definition of these parameters. That way you're just not twisting knobs on your reverb and hoping for the best. Let's look at pre-delay. So here's a pre abbreviation on this reverb plugin. This is the amount of time that transpires between the primary sound and the sound of the first reflections. So imagine you're hearing my voice. It's echoing off that wall and coming back to your ears and combining with the direct sound. The amount of time that takes, that's the pre-delay. So if you set this longer, that means that your dry sound gets to exist naturally before the reverb descends upon it. But if you set this super tight and fast, the reverb is just on top of everything. So you might want to set a longer pre-delay time for vocals, say, so that the words and the syllables are still clearly delineated. Okay, then we have initial reflections. These are early echo repeats that are a lot like delay before the sound blends with the primary sound. So you might hear a little bit of echo repeats before it blends into one all-encompassing ambient sound of reverb. A little bit of delay before the delay descends into reverb. That's what initial reflections are. Okay, room size, which is the most obvious one. It combines several parameters to simulate a specific room dimension. When adjusting room size, the sound will be layered to mimic a hall or a chamber, bathroom, tunnel. Nice and easy. And finally, reverb time. Sometimes it's labeled as decay. It measures the time it takes for the reflections to drop below 60 dB, which means become inaudible. So how long do you want this ambient reverb to continue after its initial contact with the primary? If you set it super long, you're going to have a bunch of residual sound, and that might make your recording sloppy. But, maybe you're doing a special effect for a horror movie or something, and then, go ahead and turn your length up super long. Okay, there are other parameters, but these are the common ones. Pre-delay, the amount of time that elapses before the reverb descends upon the sound. Initial reflections, these are echo repeats that occur before the sound becomes ambient, like reverb. There's a room size, think cathedral, church, hall, theater, etc. And then there is reverb time, which is how long the reverb continues to exist after initial contact with the primary. There are 4 basic kinds of reverb. There is plate, digital, spring, and acoustic chamber. Plate reverb is a mechanical device featuring a thin steel plate suspended under tension and affixed with a transducer. Think of a massive piece of sheet metal, something like 5 feet tall by 7 feet long. And affixed to it you have 2 transducers, one that plays the sound into the piece of metal and another one that recaptures the sound. A little contact microphone. Think about how resonant a piece of sheet metal would be if you just shake it, right? You can simulate thunder. Well, if you get sound reverberating through the sheet metal, that'll create a pretty extraordinary kind of reverb called plate reverb. Nowadays, of course, plate reverb is simply simulated in digital reverbs, and we'll come to that presently. Another type of reverb is acoustic chamber. This is created by playing audio via loudspeakers into a large room. Think if you had a pre-recorded sound and you're playing it out of a loudspeaker situated here, and then on the other side of the room you have a microphone set up. So you're playing the sound into a large room, the sound is interacting with the large room, and the microphone on the other side of the room is capturing that interaction. Now this was the standard issue way to create reverb until the advent of digital signal processors. This was Studio 3 at EMI where the Beatles recorded. Motown had an acoustic chamber. And this is responsible for some of the most lush and natural sounding reverbs in recorded history. You can imagine how nice your reverb would be if you find a perfect room and you set it up with a speaker and a microphone in this way. Another type of reverb is spring reverb, which is essentially the same as plate reverb, wherein you have 2 transducers on a piece of resonant substance. Just imagine instead of a piece of sheet metal, you have a spring. Now this is what's operating inside of guitar amplifiers. The spring vibrates along with the sound that's been piped through it, vibrates sympathetically, and then you recapture those vibrations and blend it with the primary. This is a pretty messy way to create reverb. Unless you're playing surf rock, you know, I have spring reverb on my amp. I just turn it off because I have a digital reverb unit on my pedal board, which brings us to the last type of reverb, the only one that matters really. Yes, it's great to know about acoustic chamber and spring reverb and plate reverb, but they're essentially museum pieces. So here's another reverb plugin in Studio One. You can basically simulate all the characteristics of plate, spring, and acoustic chamber, operating fully inside your computer. Okay, dynamic processors deal with the amplitude of sound. And common ones include compressors, limiters, expanders, and gates. Now, in reality, compressors and limiters are the same devices. So this is a compressor. If you turn the ratio up high enough, it just becomes a limiter. So too with an expander. An expander, if you turn the ratio up high enough, just becomes a gate. So that's nice. There are only 2 dynamic processors. If you turn up a compressor high enough, it becomes a limiter. If you turn up an expander high enough, it becomes a gate. Okay, let's start with a compressor or a limiter. A compressor is used to control excessive volume by restricting the signal's output amplitude. So if a recorded signal is steady around 30 dB, it's very quiet, say, but at one point the track jumps up to 70 dB, then any uncompressed mixing of this track will be beholden to that 70 dB transient, which is going to be a problem. You won't be able to turn up the 30 dB sound appropriately loud enough because there's that monster waiting for you down and later in the track, that 70 dB transient. That's no good. You need to use a compressor. Now, a compressor will decrease the difference between loud and soft. So you had one at 70, one at 30, just a huge difference, right? 40 dB. A compressor will shrink those differences, thereby making the track useful because it's been controlled. If you're trying to mix a song and you have a track that has that big of a difference, it is going to be useless to you. You won't be able to do any adjustment to that track because it's all over the place amplitudinally. So a compressor decreases the difference between loud and soft. Say that to yourself until you understand. Explain it to your grandma. Decrease the difference between loud and soft to control amplitudinal variation in a sound. So you want to create a good, predictable sound that then can be turned up. So once the sound's been controlled and has been tightened into a pocket, been compressed into something that's more consistent, then it can be turned up, giving you powerful bass, powerful kick drums. Okay, let's take a look at some of the knobs you'll find on a compressor, because this was another unhappy experience. When I first began trying to process and produce music, I had no idea what these knobs were. Let me see if I can give you a hand here. Ratio, threshold, attack, and release. Let's start with ratio. Ratio determines how severe the compression is, right? The degree of compression. For example, a compression ratio of 2:1, this one's set at 7:1, but imagine it's set at 2:1, means that for every 2 decibels increased by the signal, the compressor's output says, yeah, you get 1. Okay, the sound tried to increase by 2 decibels, but that sound's going into a compressor with a 2:1 ratio. The compressor says, yeah, I don't care that you want to go up by 2, you're only getting 1. Okay, imagine if it's set at 7:1. Right, so every time the sound tries to increase by 7 decibels, the compressor says, yeah, I don't care, you get 1. You get 1 dB of increase. The sound is trying to reach for the sky. The compressor says, yeah, I don't care, you don't get to do that. It's fantastic. That's the ratio. Right, good place to start if you're just experimenting, 4:1. 7:1 is good for a kick drum, maybe something like 6:1 for bass, maybe a little bit like 2 or 3:1 for vocals. A limiter, by the way, is a ratio of 10:1. So if you turn that ratio up to 10:1, the compressor becomes a limiter. Okay, the threshold setting adjusts the amplitude at which the compressor begins working. You see the hovering white dash? That's RMS, or the average intensity. Set it -15, and notice that that is definitely in contact with the amplitude of the audio. If I set the threshold lower, it's in even more contact. And notice the reduction meter springing to life. This is the compressor operating at 2:1. Every time this sound tries to increase by 2, it actually only gets 1. Just not as many differences between loud and soft over here. Dial this up even higher. 0.7:1. Threshold set about -20. Now if I have the threshold set way up here, -4. Right, this sound is about -24, but my threshold is set at -4. That means the compressor is not on. So you might turn on your compressor and say, yeah, I'm using compression, but you're not using compression. That threshold setting is massively important. You have to sync it into the RMS of the amplitude. In fact, that's usually what I go for. RMS around -18 or so here, so I'll probably set my threshold. And that gives you a nice, steady, smooth sounding compression. Okay, attack. Attack is another important setting on a compressor. It determines how soon the compressor descends upon your amplitude with the compression ratio. If you have it set slow, the sound gets to exist for a second before the compressor lays on top of it like a blanket. So if I have this attack set at -5 milliseconds, it's just instantaneously on. Now, sometimes you don't want the compression to step on the attack of a sound. The attack is the initial impact, right? The hammer hitting the piano string, that's the attack. Oftentimes you want that attack to exist and then the compressor to come a little bit later. So you would set a slower attack setting. 40 milliseconds, that works pretty well for kick drum. In fact, this is my kick drum formula, a super simple and generic kick drum setting for a compressor. 7:1 threshold, where the threshold is, that will always change depending on your amplitude. And then a slow attack, so the kick drum gets to exist for a second and then the compressor descends upon it. In my experience, if you have the attack set too high on a kick drum, then your kick drum just sounds like it's blowing raspberries. Just a bad sound. Whereas you slow the attack, then you get that dull, thick thud of a kick drum that is desirable. Let's see, one more setting, release time. Release. Release time is how long it takes for your compressed signal to return to uncompressed parameters after the signal has sunk below the threshold. As soon as the sound is no longer in contact with the threshold, how soon does your compressor turn off? That's release. The combination of compression and limiting can add power and loudness to a sound. That's the main use of a compressor. But there are other uses. A compressor can be used to minimize the wide difference in loudness caused by musicians not maintaining a consistent distance from the microphone. If I go in and out of distance from this microphone here, right, I'm moving around on stage and trying to put on a show and be fancy. And that's going to be a problem for the mix engineer, so a little bit of compression can help smooth that out. Compression can also smooth out the attack of guitars and basses and drums and horns. If you're recording field audio for a movie and you have jangling keys, this transient, loud, shrill sound, a compressor can help control that. It can improve the clarity of speech. I'll likely process this video here with some compression. Compression used on vocals brings them forward in a mix. That's a powerful way to improve the quality of your audio. Just add some compression to your vocals. Then all of a sudden they're controlled and in a pocket and thick, and you can turn them up and make them hyper present. And a limiter prevents a sound from saturating a recording. You don't want some bully to take command of your recording and ruin it. So compression and limiting will help control saturation. Okay, one more signal processor here, and that is the expander, or the gate. They are the same. It's another signal processor in the dynamic category. So expanders and gates, like compressors and limiters, are the same devices as one another, differing only in degree to which they affect the sound. Now, instead of reducing the difference between loud and soft like a compressor, an expander increases the difference between loud and soft. So imagine a recording of a person being interviewed at a sporting event. The person's voice, if they're close enough to the microphone, should be the loudest thing, but as soon as that person is not speaking anymore, there's this ambient tornado of crowd sound underlying everything. Now, it should be a little bit quieter than the person speaking, because the person speaking is using the microphone at close range. So an expander could be used to decrease the sound of the crowd when the person's not speaking. The person pauses between words, and the expander descends upon the sound and turns it down. Let me show you what I mean. Expansion is often useful with kick drums. So I have an expander dialed in here. And every time the sound is not occurring that I desire, which is the kick drum, the expander is turning it down. This meter here is showing you a decrease in volume. We can have it set even higher. So now it's severely decreasing volume. So it's turning down that crowd sound. The person's not speaking. The expander is crushing that crowd sound. We don't want the crowd sound. We want the person speaking. And in this case, I don't want the rest of the drum set. I don't want the sound of the band in the room. I don't want the sound of the tom-toms or the cymbals. On my kick drum track, I want kick drum. So an expander can help you achieve this. And if an expander isn't quite working, then you can use an expander turned up at a ratio of 10:1, also known as a gate. Now, instead of just turning the sound down, generally speaking, a gate will turn the sound off. Set this range super low. So every time the kick drum's not sounding, the gate is essentially turning the sound off. The open threshold works just like the threshold on a compressor. You decide the sound at which the gate allows the desired sound through. If you have it set too high, it's never achieving -4 dB. So the gate is just turning everything off. Then if I slowly back this up, we can see that the kick drum begins poking through. Nice. That's what we want. And when the kick drum's not poking through, the gate is turning the sound off. Okay, an expander and a gate increase the difference between loud and soft. Okay. Okay, in conclusion, equalizers, reverbs, and dynamics are the most common signal processors. You'll use these three in just about every audio project you engage in. As you can probably imagine, there are many more effects, but they're not nearly as common as these three. Like reverb, the signal processor called delay is the progenitor of these other effects. So effects like chorus, flange, phase, they're all delay based. They're all essentially manipulation of a delay. And I'll cover those in a later presentation. But thanks for watching. I hope that you got something from this video. Until next time, this is Brian Jump.